Hello, EnvoyCon. Hi, I'm Tony Allen. I work in Google Cloud's networking group, um, and I'm going to talk to you today about the wonders I have seen. Things that make the most jaded among you remember what it feels like to be excited about technology. My team, we're building the glorious future of service networking, and let me tell you, where we're going, we won't need sidecars. I'll tell you how we pull this off. So sidecars, I think everyone's familiar with sidecars, but since most of the things we talk about today are like AI and LLMs and this and that, I'm going to remind everyone about good old-fashioned sidecars. So, you have a Kubernetes node. There's pods on your node. Each pod gets an Envoy sidecar, and that's what I mean when I talk about that. We got first-class support in Kubernetes via native sidecars. It was stable in version 1.33. That was April 23rd, 2025. So it's pretty wild given how long we've been talking about sidecars. Let me put that in perspective. We've been talking about sidecars since at least 2015. So we'll transport ourselves back there. Uptown Funk is #1 on the charts. People are listening to it on their new iPhone 6s with the buttons. Okay. Kubernetes hit 1.0. in 2015, and it was donated to the newly formed CNCF. Okay, Brendan Burns, he still works at Google. He's writing blog posts and talking about sidecar containers. So there's a link to that, if you want to check that one out. Here's a fun fact. There were also ambassador containers, which are really more relevant for Envoy, because, Envoy sidecars they're proxied local connections to the world. It's a fun read. Check it out. Fun Kubernetes history. We've been around for a while, I guess. We've been doing this for a while, long enough that we have some notes on sidecars. Okay. One of those notes, resource usage. It's they're starting to annoy people with all of these CPU reservations. People are provisioning it for peak loads, and if you don't use the requested resources in your proxy, they're just taken. They're occupied. Sidecars are also operationally complicated. Deployment, requires you to inject things into your pod spec, and it's a whole mess. If you want to upgrade your sidecar, let's say you got a CVE, okay, you need to upgrade Envoy. What do you got to do? You got to roll all your pods. Okay, if you're a cloud vendor and you do some kind of hosted service meshy type thing, it's a real pain. No one likes doing that, and customers don't like it happening. And the sidecars are invasive. I don't think there's any application developer that is excited to see these proxies, or to deal with the complications that arise from them. So don't worry, we have a solution now. We're just going to make it a daemon set. Problem solved. Single proxy for the whole node. All the pods will share that one proxy, and it'll have less resource usage. One reservation, okay? One pod's unused resource budget can be used by all the other pods. Operations are hopefully simpler in this case, right? We don't have to modify pod specs. If you need to upgrade your proxy, you just upgrade the proxy. You don't have to bounce the pods, and it's less invasive. So. It's pretty cool. That's where we'd like to take things, and this was a totally original idea that we came up with ourselves. Okay. Istio's been on this for a while. Turns out, Ambient Mesh is doing that with Istio. I know this is EnvoyCon. Bear with me here. Okay, they brought up this Z-tunnel thing. Z-tunnel is an L4 proxy in the Istio ambient situation. It's an L4 proxy that sits on the node. It just does like MTLS. It's very minimal, right? It's very fast. It's purpose-built, and it's written in Rust. So, rip out all your envoys, set them on fire. That's not true. I read these blog posts, and it makes sense. It makes sense to use a Z-tunnel for those cases, but my team, my org, my group, we're not using Z-tunnel for our node scoped proxy. I'll tell you why. Okay, Google has a lot of infrastructure for managing envoys. Custom filters, kernel optimizations. There's like a security team and researchers just poking at the thing all the time. There's an entire Envoy platform team. We've got all these deep integrations with Google Cloud just, baked into Envoy. And Envoy is super extensible. Like if there's something that we want to change about it, right? There's all these extension points that we can just re-implement entire, parts of Envoy if we want to. Okay. These are all valuable assets. We don't want to give them up. And also, we just don't want to deal with it like another proxy. One's enough for us. Let's see. We're going to make it work. So today, I'm going to tell you about what we did to pull this off with Envoy, the types of changes we had to make in there, you'll see what it took. So, after reading all those blog posts, I sat down and I was thinking to myself, like, okay, what do we need to do to Envoy to make it like at least as good as dtunnel? Like, we don't have to compile in all the L7 HTTP connection manager, so we'll just pull all of that out. We'll just have a good old-fashioned TCP proxy, and we'll put it as a daemon set, and then Bob's your uncle. That should work, right? So it wasn't that simple. Problems we had to solve. Configuration was one of those. So, like, what does that even look like? When you configure a node level Envoy versus a sidecar, right? And scalability and performance. Because when I read the blog posts from Istio, they just keep talking about performance and this ztunnel thing, and I'm really attached to Envoy, and it hurts my feelings. So I want to be at least as good. Okay. So let's go. Let me show you. Let me show you how we did it. Let's start with a simple sidecar config. So Akshida's talk just before this, super useful. So thank you wherever you are for that, because this will make sense to everyone now, hopefully. Let's run through it. I'm going to show, instead of showing you like a YAML hellscape, I'm just going to show you these blocks, which you can sort of replace each one with YAML if you really want to. So we would specify in the listener what is the port that we want to listen on, and the address. Listener filters would come next, right, inside your listener, and then the network filter chain. So in our case, for this node level proxy, we use the TCP proxy filter among some other things, but the most relevant one here is going to be the TCP proxy one. And then there's a cluster config. That's where you put your load balancer and your transport socket config, which would have like your certs and TLS context, all that jazz. So when you have a sidecar, okay, you basically have an Envoy in your pod. Okay, so you have your node, an Envoy inside the pod, and then your config would look like that. It would be pretty simple. You're listening on some port, traffic gets redirected to whatever that local port is that it's listening on, and then proxying happens, and then it's sent out of the pod, out of that ETH0 interface, right? So we need to pull the envoys out. So how are we gonna do that? We have this problem, which is things get a little weird. How do we get traffic to the proxy if it is not inside the pod's network namespace? Okay. The answer here would affect the shape of our config, like what the configuration is going to look like. So let me take a quick detour. What is a network namespace? Okay. The Linux kernel, if you go like CLI into a man namespaces, right? You can read all about it, but there's a whole bunch of different types of namespaces. One of those is a network namespace, and it's basically just like an isolation mechanism for for the network stack. When you go into a Kubernetes pod, and if you shell in, right, and you do like a, I don't know, netstat or something, you'll see that there's only a few things that would be in there, right? Or like you do a PS and you're like, I'm the only process on this node. Like, no, you're in a namespace. Everything's hidden. So each network namespace has its own set of network devices, IP address, routing tables, firewall rules, right? So if you like mark a packet inside your pod and it gets sent out, like you can't have like firewall rules outside your pod, because that packet mark only means something in the context of the network namespace that you did it. Sockets also. It's got its own set of sockets. This is going to be relevant in a second. Okay. So how can we get traffic out of a pod into a network namespace that the Envoy is in, right? So the Envoy can proxy it. Here's one way. You can do eBPF redirection, right? There's a bunch of redirection helpers. Okay, there's that list of function calls over there. So if you're in an eBPF program, you have this available to you to use. There's just one of those that will work across network namespaces, and that's BPF redirect peer. That'll basically, you take your program, attach it to some interface, right? And then when you do a redirect peer, you can redirect packets to another interface somewhere else in another network namespace. If you have the freedom to just attach eBPF programs wherever you want, it's not a bad choice to do this. You should consider it. That's not what we did because we don't have that sort of freedom where I'm from. So we taught Envoy about network namespaces instead. So here, we started here. We said, okay, well, let's make Envoy network namespace aware. First things first here. Let's add a network namespace parameter to the socket address proto, right? So if you look when you're in the listener or like an Upstream or whatever, whenever you specify like an IP address and a port value and a protocol, now we have this cool network namespace file path field. It's only relevant on Linux, obviously, but that's there now. So we'd be able to make use of it. How would we do that? Well, let's look at some code. You don't need to really grok all of this. It's just that first one there. We get a file descriptor for the network namespace. So normally, when you specify a network namespace, it's like /var run netns, and then it's just like a bunch of files that represent network namespaces. Get a file descriptor. There's a really cool syscall called setns. Right? And what that does is, it'll take that file descriptor, and then you tell it what kind of namespace that is that you're trying to change there. And then, sorry, oh geez, I'm so nervous. What it does is it'll take the current thread that you called that from, and then jump to whatever that namespace is that you would like it to. So you set the namespace of the thread that you're executing this syscall in, right? Here's what's cool. You can create a socket in that network namespace now, okay? So when you jump over your threads in another network namespace, create the socket. That socket lives in the network namespace it was created. So now we can jump back, to our original network namespace, but keep the socket. And now we're in a different network namespace, but we have a socket that's listening somewhere else, which is pretty sweet and useful for our purposes. So how do we use this? In the listener, that was merged, which basically all it's doing is in the listener, when you specify an address or the additional addresses, like what IP and port am I listening on, you can also specify the network namespace, and now Envoy can listen in just arbitrary network namespaces, as long as you have the permissions, obviously. But that was pretty sweet. Next thing we did, we modified the upstream. So inbound connections handled by the listener, right? On the upstream side, when we want to open a connection and send it out, we thought to ourselves, okay, well, if this Envoy is sitting outside a pod's network namespace catching traffic, do we want to send it out from the Envoy, or do we want to send it out from the pod? Well, we want to send it out from the pod. We want it to look like sidecars for a bunch of reasons. One of those is network policy enforcement. In cases like Cilium or something, right? On the ETH0 of a pod, traffic is going through. It's like a VETH pair. As it's going out through the pod's ETH0 into the host, network policies are enforced there. We just don't want complications, so we're just going to send it back out through the pod. So that's why we had to do this change. In the cluster config, there's a field with the name bind in it. I forget the name, but this is the bind config that you would specify there, right? You specify source address, right? And from a few slides ago, you saw that wherever you can specify an address, you can specify network namespace. So now what that'll do is when you open a connection to something in the cluster, right? So like some endpoint or whatever, it's going to open the connection from the network namespace that you specify. So what Envoy is doing is it jumps over to the network namespace that it needs to for that bind address, creates a socket, opens connection, jumps back, which was pretty cool. So this is what it lets us do. This is how we get traffic into Envoy in our case, right? We have a listener per pod. This is like the most ham-fisted way to do this. Like there's way better ways to build your config, but for the purposes of this talk, this is how I'm gonna talk about it. So for each pod gets its own listener, okay? And that listener listens in an address inside the pod's network namespace, right? This is kind of nice because if we had a single listener with a bunch of addresses, one for each of the pods, anytime like a pod comes up or down, that would be a config change for the listener, which cause all your connections to drain. And that's pretty bad. Like every time a pod comes up or down, you don't want to just drain all the connections for people who were sitting there just minding their own business. So that's why we did it this way. But it's not optimal. Well, I'll talk about that later. So the traffic flow, it looks kind of like this now. Okay, we have some net filter rules that will catch outbound traffic, redirect it to some local port that the Envoy is listening on, goes into the Envoy, does its policy enforcements or whatever Envoy does, and then sends the connection back out through the pod, and it's ETH0. So iPerf tests. We wanted to see like, okay, well, we built this config, we did this. Is this like something that we'd be able to actually use, or should we just throw in the towel and just figure out how to get ztunnel in there? So here's how the test works. Okay, we just create like some number of services, right? So let's say you have 10 clients, 10 servers, and iPerf is you have one client, one server. And that's it. It's going to send a whole bunch of traffic, and it can do it bidirectionally. We create a service for a client pod, a service for the server pod, and then we basically duplicate this however many times. Okay, each client would open, and I don't know, anywhere between like 32 and 128 connections, depending on the test we're doing. And all this graphs I'm about to show you, we tested on just like 2 of these C2D high CPU 112 VMs, 112 vCPUs. So that's how many worker threads we had. Really pushing it, and 224 gigs of RAM. This was really expensive. I was running these tests, and I get an email like a week later because I triggered some finance alarm. It was like, and they were like, "Tony, did you know that this is happening?" And I was like, "Oh, geez, let me fix that." But I got my data, so let's check it out. So we had in this particular test, right? This was like we had just built the thing, we got some traffic flowing, and we're like, oh wow, I can send traffic from this pod to like that other one, and it goes through this node level Envoy, gets sent out, gets caught by another node level Envoy, goes to the pod, and it comes back. That was it. We just wanted to see how it did. The test, we had 150 listeners, and if you remember from before how we built our config, that was about 150 pods for one node, which had one Envoy, and about 4,000 clusters. Okay, and I just pushed as much traffic as we could. So that instance, it had a 32 gigabit NIC, which I mean it's a virtual NIC, but we pushed 32 gigabits a second through the Envoy with those numbers. Let's check it out. Yeah, it wasn't great. So if you look on the left there, if you can read that, that is the memory allocated as measured by Envoy, right? So when you look at the Envoy stats, it's like a server dot memory allocated or something like that. That's the value that we have there, right? On the right is the heap memory. Okay. So 4.5 gigs of memory is not great, in my opinion. I thought we could do better. So we were like, all right, well, let's see like what the, what's eating up all of our memory over here. That's pretty, let's enhance. There we go. Raw buffer socket, okay? If you remember from Akshita's talk, she's talking about those buffers, right? This is it. This was the culprit, or at least, one of the optimizations we had to make. There were a bunch of them. This one was the best bang for buck, okay? Ran some tests just to check out, like, let's just make sure that, like, it really is the buffer. So we, like, add some more metrics and, and check it out. It was like 60% of the used memory when we were pushing that much traffic through the Envoy was just buffers, which makes sense, because if you remember from that last talk, when you have these like high bandwidth connections, right, Envoy has to do all this buffering and gives back pressure. By default, that buffer size is 1 megabyte. There's a little warning in the Envoy configs, if you guys ever check this out. It says, in the presence of untrusted downstreams, you should probably set this to 32K. And there's a little, in the documentation on the Envoy docs, there's like a guide for using it as a front proxy. It tells you some changes. This is one of those changes. And this is why, because of all the memory usage. Somebody can just open a connection and then blast you with traffic, right? And eat up a bunch of memory. We don't want that. So this is what we did. We set this, and then there's also one for the upstream as well, right? So there's a downstream buffer that you can limit, and then an upstream buffer. We ran the test again. I'm just reusing some data that I'd sent around internally. So this was a slightly different test, right? But we had about 25,000 connections, right? And we cared about the number of connections because we knew that the memory usage was based on the number of connections that we had. There was a significant improvement in memory usage. Let's see. So when we had the 1 megabyte buffer limit, that's the column on the left, the 32 kilobyte buffer limit, column on the right, and I limited it to 16 workers because finance, I don't want to email again. So let's see. Memory allocated. So with 25,000 connections, we were pushing more traffic through, right? If you look on the left here in the top left, it was about, I don't know, like 5, 6 gigs, something like that. When you limit the memory, in the top right, it was like stable. So we like saturated the available buffers that we had available to us, and it was like like 3.5 gigs, which wasn't bad. So that was a good improvement. The one in the middle, the columns in the middle, that was like the amount of memory being eaten up by the buffers themselves, and then the one on the bottom is just showing you it was 25,000 connections for real. We did another iPerf test. But this time it was like supposed to be something a little more realistic. So we're like, all right, let's get an instance with a 32 gigabit NIC. We will push 12 gigabits of traffic through it, but we'll still have like 25,000 connections. Okay, so on the top, you can see it's about like 12.5 gigabits a second per node. And each one had about the same number of connections. So looking at, this is a different graph because we realized, okay, Envoy will report some memory usage, but in reality, Envoy doesn't know like what the kernel is buffering for the sockets. And it turns out that the kernel buffering in the sockets was significant as well, so we had to adjust those. So after doing that, we saw that we were able to get, I don't know, sorry. This is an aggregate for 4 Envoys. So we're using about 4.75 gigabytes of memory for 4 Envoys. Divided by 4, it's a little over a gig per Envoy to push 12 gigabits at 25,000 active connections. I thought that was pretty good. So that's sort of where we ended up. Now, let's see how we doing on time. Okay. I'll take some questions. There's more information, but I figured this is a good place to stop if anyone was wondering about anything in particular, because this is a Envoy community. I'm sure we have questions. Did someone say something? I can't hear. Did we beat Z-Tunnel? Is that what we get up there and ask? I was waiting for that question. Whatever. I really want to show you. Yeah, we did. Check it out. This was ztunnel out of the box. Okay, this wasn't like a fair. I didn't optimize ztunnel because I didn't care. But so ztunnel, Istio, CTL, whatever, enable ambient, the exact same cluster, exact same test you saw before. Envoy was using like 1 point something gigs of memory, right? Per Envoy. This was so it used like 40 gigabytes divided by 4. So each ztunnel was using like 10 gigabytes, which is wild. I was like, I did not realize that. I didn't expect that. I thought ztunnel was going to wipe the floor with us. And then here's my favorite part. I just was like, well, my job is done here. I go home and I leave the test running. I came in the morning just to look at it again and feel good about myself. There was a memory leak in ztunnel. It just kept climbing. So we should have probably reported that one, but I'm sure they'll figure it out. So yeah, I was real happy about that one. This was the latest release as of October 24th, 2025. So whatever the cluster pulls. I don't know what that is. So I look forward to getting roasted in a blog post by them. But yeah. Next question.
Yeah, I got a question about how you ensure that the IP table rules are set up when, say, a pod restarts or starts.
Yeah, great question. No, that's good. I just totally left it out because it was complicated. But I'll tell you. So we have a node level Envoy, right? Okay. There's all this complicated stuff like what you said. Like, okay, well, when a pod comes up, you got to install the IP tables rules. You got to make sure that it's not just going to be marked ready to roll and send traffic, and it could potentially bypass the Envoy. And we have like security policies we want to enforce, right? We have like a sidecar for the Envoy, which is just silly. It's another daemon set that's sort of like a control plane agent helper type deal, and we have a CNI plugin. So pod comes up, the CNI plugin is going to run, right? And to set up the network. What it'll do is, in that CNI plugin, we have access to a lot of information. One important piece is, what is the network namespace of the pod that you're in? So we send a request to the little agent that lives on the node over a Unix domain socket. And then it configures all the rules for that specific pod. So that agent will jump into the network namespace of the pod, set up the IP tables rules. NF tables is what we use because it's the future. And then it jumps back, and then we program the Envoy. So we're like, hey, make your listener, that's the network namespace that you want, right? And then inconveniently, with XDS, like you'll send Envoy its config, and Envoy acts back with the via XDS, and XDS act. It doesn't mean it applied the config. This is like everyone's annoyed by this. So what we had to do is that right now, because we're still developing it, this hacky thing where we just sort of like keep looking at the config dump and trying to find what we're looking for. We're like, looks good, all right, bring the pod up. And that's that. Yeah.
So are you guaranteed that by the time the pod starts, the CNI rules will be set up by the daemon set?
I see. If a pod's already up and then we like sort of install this stuff?
No, it's like if you make a new node, right? Your daemon set's going to run to configure the CNI.
Right.
What if the pod starts before that configuration is written to the CNI? Because we have the same problem in Istio too, actually. So I'm curious.
I mean, if Istio has that problem, we almost certainly do.
Okay.
Yeah. Cool. I look forward to figuring it out with you.
Great talk.
Thanks.
So you didn't talk about isolation, which I thought maybe you might have.
Oh yeah, isolation. That's a whole can of worms. Okay. The last Envoy talk, or last EnvoyCon talk I gave was about sort of like load shedding and that sort of thing. For isolation, let's say you're worried about noisy neighbors, right? Yeah, that's a real problem. Envoy doesn't have a mechanism right now, but you can put it in there, right? So what we're planning to do, which we're still building it, is have an extension that does this. And then we're thinking, we just have like a fair queue or something. The overload manager, there's one of the settings in there that lets you sort of just kill connections that are the most expensive ones, right? We'll just make an overload manager change that lets us kill connections fairly. And that's how we're thinking about doing it. But we haven't done it. We haven't run tests to see if it actually works. So that's just the plan.
Sure, makes sense. And I guess you also mentioned about being able to upgrade your proxy and stuff like that.
Yeah.
How are you doing that?
Yeah. So let's see if I can go back to that little config thing we got there. There's also a zTunnel blog post where they do the exact same thing because it's just a great idea, and we totally ripped it off from them. But what's nice about this type of way of doing it is you can have two envoys up side by side listening on the same port in the pod, right? So what'll happen is the old envoy is up and it's listening and it's taking traffic. The new envoy comes up too. It starts listening on that same port. You use the SO reuse port, and then it just sort of the kernel will figure out which socket to do it on, and then the old one just sort of starts draining and stops accepting connections. The new one's now taking all the connections. The old one will drain, and then it'll die gracefully.
Cool, thanks.
Man, I had the exact same two questions that he stole. So a little bit more on isolation. Is it possible to use connection limiter? Like if you can have n number of listeners.
Like the connection rate limit filter?
Yeah, I think there is a connection limiter.
Yeah, that's a listener filter.
Yeah.
Okay. So in that one, you could. I think there's a way to do that. So if it's a listener filter, right, you have the on accept, right? And the way that we do, there's a global connection limit, like a runtime variable or something, right? The way that works is we'll accept the connection, then we'll be like, oh, should we do this? Oh, never mind. No, kill the connection. So there's logic that we can build in there, right? So we're going to have some sort of global data structure that's tracking where these connections are coming from, right? And then we'll have to figure that one out.
Okay.
Yeah, I don't have time. Sorry.
Yeah,
We can chat though. All right. I gotta go. But we can talk. I'll be here all week. Thanks.